Section 4.7 L'Hopital's rule. L'Hopital's rule for the form of 0 divided by 0. Let's begin with section 4.12. Theorem 4.12 reads, suppose f and g are differentiable on an open interval I, containing a with g prime of x not equal to 0 on I, where x is not equal to a. If the limit as x is approaching a of f of x equals the limit as x is approaching a of g of x equals 0, then the limit as x is approaching a of f of x divided by g of x equals the limit as x is approaching a of f prime of x divided by g prime of x. So in other words, we're going to apply the derivative to the numerator and then separately apply the derivative to the denominator. And from there, hopefully, we should be able to find the limit. Let's go ahead and take a look at an example. So example 1, evaluate the following limits. The limit as x is approaching 1 of x cubed plus x squared minus 2x divided by x minus 1. Okay, so the problem here is when I substitute in the value for x, we get 0 and thus have an undefined value. While we can counteract that and find limit by applying L'Hopital's rule. So to do so, let's go ahead and take the derivative of the numerator. So we consider this to be our function f for our numerator and our denominator is g. Let's go ahead and find the derivative. For our numerator, we have 3x squared plus 2x minus 2. And for our denominator, we have just 1. We're trying to find the limit as x is approaching 1 of our function. We took the derivative of our numerator and our denominator. Now we can go ahead and directly substitute that 1. All right, so we see that we get 3 times 1 squared plus 2 times 1 minus 2 divided by 1. We get 3 plus 2 minus 2 over 1. Our final answer is just 3. And there you have it. That's the wonders of L'Hopital's. B. The limit as x is approaching 0 of square root of 9 minus 3x minus 3 divided by x. Again, we're going to treat our numerator as a function and then our denominator as a separate function and find the derivative. Let's do that work above. So if we make our numerator f and our denominator g, our derivative of our denominator would be 1. Now for our function f, our derivative, we have to do chain rule, right? So if we rewrite it to be, for f, if we rewrite it to be 9 plus 3x raised to the 1/2 power minus 3. Remember, for chain rule, take the derivative of the outside, then multiply it by the derivative of the inside. So we have 1/2 times 9 plus 3x times, well, minus 1, negative 1/2 power, times 3. All right, so now we have our derivatives. And we can actually rewrite this. So we can write our negative exponent as a denominator. So that we have 9 minus 3x square root, and then a 3 in the numerator, and the 2 stays with my denominator. Okay, now we have our derivatives. Now let's go ahead and try to apply the limit as x is approaching 0 of 3 over 2 times the square root of 9 minus 3x divided by 1. And now we don't have a problem. We can go ahead and directly substitute the value of 0. So that we have 3 divided by 2 square root of 9 minus 3 times 0 all over 1. So we have 3 divided by 2. The square root of 9 is 3 divided by 1. 3 divided by 6 divided by 1. Well, 3 over 6 is 1 half. 1 half divided by 1, or anything divided by 1 is itself. So our answer is just 1 half. In a special note, L'Hopital's rule requires evaluating the limit as x approaching a of f prime of x divided by g prime of x. It may happen that this second limit is another interminate form to which L'Hopital rule may be applied. Okay, so let's go ahead and apply L'Hopital's rule. Let's go ahead and take the derivative of the numerator and the derivative of the denominator. So before we start, recall that the derivative of secant of x is secant tangent. Secant times tangent of x. Okay, so let's go ahead and take the derivative. If we take the derivative, we have the limit as x approaching 0 of the derivative of secant is secant times tangent. The derivative of 1 is 0, and then we're left with 2x on the bottom. Now, I still have a problem. When I substitute that value, I still get 0 in the denominator, thus undefined. So because of this reason, our next step is to apply L'Hopital's again. Okay, so let's take the derivative of the numerator and the derivative of the denominator. The derivative of tangent, to help you recall, the derivative of tangent is secant squared x. Okay, so let's go ahead, now that we have that fresh in our heads, let's go ahead and find the derivative. So in our numerator, we have to go ahead and proceed with product rule. So the derivative of secant is secant times tangent. Times our second, which is just tangent of x, plus our first, secant of x, times the derivative of our second, which is secant squared x, divided by the derivative of our denominator. The derivative of 2x is just 2. And don't forget the limit as x is approaching 0. Okay, let's go ahead and clean up our numerator. I see we have some values that are multiplying by themselves, so we can raise them to a power. So I have the limit as x approaching 0 of, in our denominator we just have a 2. From the numerator I see I have a tangent times tangent, so I have tangent squared x times secant of x plus secant times secant squared, secant cubed x. Okay, now we can go ahead and directly substitute in the value of 0. Just so that you have these values handy, secant of 0 is equal to 1, and tangent of 0 is equal to 0. Okay, so we're left with, well, tangent is 0, so it makes all of the 0. 0 plus 1 all over 2. We're just left with 1 half. B. The limit as x approaching 2 of x cubed minus 3x squared plus 4 divided by x to the 4th power minus 4x cubed plus 7x squared minus 12x plus 12. All right, well, we see that if we try to directly substitute in a 2, we're left with a 0 in our denominator, thus undefined. Let's proceed by applying L'Hopital's rule. All right, by using L'Hopital's rule, we'll take the derivative of the numerator and the denominator. So we have the limit as x is approaching 2. Let's take the derivative of the numerator. We have 3x squared minus 6x. In our denominator, we're left with 4x cubed minus 12x squared plus 14x minus 12. Now, again, we're in a pickle because if I plug in a 2, I get a 0 from our denominator again. And that's a problem. Our denominator is equal to 0. So, according to our notes, we can go ahead and apply L'Hopital's again. So let's go ahead and apply L'Hopital's again. So that we have the limit as x is approaching 2. The derivative of our numerator is 6x minus 6. In our denominator, we're left with 12x squared minus 24x plus 14. Okay, now here we're left in a situation where I can directly substitute in the value of 2. So that I have 6 times 2 minus 6 divided by 12 times 2 squared minus 24 times 2 plus 14. All right, we clean that up. Our reduced answer, our simplified answer is 3 over 7. That is our limit. Let's continue for a situation where we may have infinity divided by infinity. L'Hopital's rule also applies directly to limits of the form of x approaching a of f of x minus g of x, where the limit of your numerator is approaching 0 and the limit of your denominator is approaching 0. We refer to this as 0 divided by 0. Theorem 4.13, L'Hopital's rule, infinity divided by infinity. Suppose f and g are differentiable on an open interval I containing a with g prime of x not equal to 0 on I, where x is not equal to a. If limit as x approaching a of f of x equals plus or minus infinity, and the limit as x approaching a of g of x equals plus or minus infinity, then the limit as x approaching a of f of x divided by g of x equals the limit as x is approaching a of f prime of x divided by g prime of x. Provided the limit on the right exists, or is plus or minus infinity. Also, the rule applies for x approaching plus or minus infinity, x is approaching a to the positive side, or x approaching a from the negative. Let's take a look at example 3. So our problem here is as we take the value of our function, and there's a typo, I'm sorry, it's supposed to be to infinity. I'll make that correction on your notes. We see that if we apply the limit to our numerator and to our denominator, they're exponentially big. So when you take the limit to infinity, it's an even bigger value to infinity. So separately, we're left with a situation where I have infinity divided by infinity. For such case, I can apply L'Hopital's rule. So to do so, let's take the derivative of our numerator and let's separately take the derivative of our denominator. So I have the limit as x is approaching infinity of 12x squared minus 12x and 6x squared minus 10. Okay, now we're still in that same situation. We still have infinity divided by infinity. Okay, well, let's apply L'Hopital's again. So that we have the limit as x approaching infinity. And if I take the derivative, I have 24x minus 12. And I'm left with 12x minus 10. Oh, constant, the derivative is 0. So just the 12. We still have the same situation. We still have infinity divided by infinity. So let's go ahead and apply the derivative one more time. By doing so, we see that we're left with constants. We have the limit as x is approaching infinity of 24 divided by 12. And 24 divided by 12, that just gives us 2. And that's our result. Let's go ahead and continue with the next example. Same situation, cotangent at 0 is an undefined value. So let's go ahead and apply L'Hopital's rule. So if I take the derivative of my numerator, a constant is just 0, so that one is gone. But for that cotangent sine of x, we have to use chain rule. Our argument is sine, that's on the inside, and our cotangent is that trig function that we are applying. So we have, for your function f, for your numerator, think of it as negative cotangent sine of x. Since you know that that 1 is going to just be 0. Okay, well, the derivative of cotangent is negative cosecant squared. So we're left with negative cosecant squared. All right, we still have the same argument on the inside. But according to chain rule, we got to take the derivative of the inside separately. And the derivative of sine is cosine. So times cosine of x. So that's our derivative of our numerator. I just wanted to slowly do it separately because it's a bit involved. All right. So we're left with cosecant squared sine of x times cosine of x. And the derivative of cotangent is negative cosecant squared, so we get negative cosecant squared of x. Now, let's rewrite this. Let's simplify this. It's a bit tricky. We're going to use the fact that cosecant is, well, cosecant of x is 1 over sine of x. So if we think of these cosecants as 1 over sine, I can go ahead and move them or rearrange them so that we can have, so that first cosecant squared, I'll rewrite it as 1 over sine, and therefore it could now be sine squared of sine of x. And that cosecant squared in the denominator is now negative sine squared of x. And cosine of x, that never changed. That just stayed there. Now this looks a lot more familiar than it did before. Okay, we still have a problem. Sine at 0 is 0. So we still have that undefined value in the denominator. Let's go ahead and apply L'Hopital's one more time. But before that, let's be clever. Let's go ahead and use our limit rules from back from chapter 2. So let's not forget to write the limit as x approaching 0 to infinity. Now our problem is only with those signs. So only with these signs here. So let's go ahead and split our argument before we apply L'Hopital's. So let's think of it as the limit as x is approaching 0 to infinity of negative sine squared of x divided by sine squared of sine of x. And then let's take the limit of cosine separately. The limit as x is approaching 0 to infinity of cosine of x. Okay, well, cosine of x at 0 is just 1. So we know that's going to equal 1. Now we're just left to work with our signs. Okay, let's go ahead and apply L'Hopital's. So that we have the derivative of sine is cosine, so we're left with negative cosine squared x. The derivative of sine is cosine again, so I have cosine squared of sine of x, and the derivative of sine is cosine. That was chain rule. We took the derivative of the inside and the derivative of the outside. One more thing. Take a step back. I factored that square, so I wouldn't have to deal with it here. So let me do that one more time. And I could erase the video, but I think it's nice to see these mistakes so we can learn from them. So instead of it being sine squared, I factor that square. Well, not factor, we wrote it, since that square applies to both the sine in the numerator and denominator. Now the argument sign, that sign in parentheses is an argument. So think of that where your pi would go, or your 11 pi over 6, or your 30 degrees. That's just your argument. The derivative of sine is cosine, so I have negative cosine of x. That square is on the outside. The derivative of sine is cosine. And we're using chain rule here. And now I have to take the derivative of the inside, so times cosine. Okay, and we know that all of that is going to be multiplied by 1, since we already evaluated for cosine. All right, keep in mind that cosine at 0 is 1 and sine at 0 is 0. So cosine at 1 or at 0 is 1. Sine is 0, so therefore cosine of 0 is 1 times 1. So our answer, don't forget that negative in the numerator, is negative 1 times 1. So that our answer is negative 1. Related forms, such as 0 times infinity and infinity minus infinity. If a limit of the form 0 times infinity in which two functions compete with each other may have any value, or it may not exist. The following example illustrates how this indeterminate form can be recast of the form 0 divided by 0 or infinity divided by infinity, which is something we know how to work with. All right, let's do example 4, L'Hopital's rule. Here is a case where I have 0 times infinity. All right, so the problem here is that we have these two competing limits. If we think of them separately as x squared and separately sine of 1 over x squared, we have a 0 times infinity case. Okay, well, I can't apply L'Hopital's rule because that would require some type of rational interpretation of a function. Well, we can go ahead and make it irrational. So this is your trick. Your trick is, well, I can make x squared into a fraction. We can make it into a fraction by writing it as 1 divided by 1 over x squared. And if you're unsure of why that is so, well, we think of this as division, right? So I have 1 divided by 1 over x squared. And how you divide fractions? Have 1 times the reciprocal, which is x squared. So it's just x squared in disguise. So let's go ahead and dress up our x squared. Let's go ahead and dress it up for Halloween. So the limit as x approaching infinity of, now here's a trick. My x squared will now be 1 divided by x squared. So we have it in the denominator. And in the numerator, I have my other remaining part of our function. So sine of 1 over 4x squared. Okay, now I can apply L'Hopital's. For the sake of making the derivative or the process of finding the derivative a bit easier, let me rewrite that denominator. So I'm just rewriting it. I have the limit as x approaching infinity, and let's rewrite my denominator so that it's x to the negative 2 power. All right, my numerator is still the same. I didn't do anything. I just took the time to rewrite it. Okay, now we can apply L'Hopital's rule. So I have the limit as x is approaching infinity. Okay, so we're taking the derivative of trig function, and we have to use our chain rule. So the derivative of sine is cosine. We keep the same argument, 1 over 4x squared. Now let's take the derivative of the inside. If you like to, you can think of it, write some notes on the side. Think of that as 4x to negative 2. If you take the derivative, it'd be negative 8 x to the negative 3, right? But we're going to be tricky. And the reason I'm doing this is because we're going to use a trick. So let's go ahead and take the derivatives step by step. So we're going to have 1/4 times a negative 2, since we have an exponent that's a negative, x to a negative 3rd power. You're like, why are you taking all this extra time? Well, we'll see that right now. Let's take the derivative of our denominator. We're left with negative 2 x to a negative 3rd. Does something look exactly the same? Yes, we see that we're left with that same value in the numerator and denominator. So they can go ahead and divide to make 1. So that we're left with only the limit as x is approaching infinity of cosine of 1 over 4x squared. Oh, don't forget that 1/4, like I am forgetting. We can go ahead and move that constant forward. So I have 1/4 as a limit is approaching infinity of cosine to 1 over 4x squared. All right, don't forget your tricks from chapter 2. Our fraction, as it's approaching infinity, it's approaching 0. So we really have cosine of 0 is approaching 1. So I have 1/4 times 1. Our answer is 1/4. One more case. the case where I'm subtracting an infinity by an infinity. So here we have the limit as x approaching infinity of x minus the square root of x squared minus 3x. The problem here is if I directly apply infinity, we're left with infinity for x and infinity for a radical. So again, I cannot directly apply L'Hopital's. We have to somehow create a fraction. So for here, let's go ahead and begin by factoring an x. Okay, if we divide everything by an x, we're left with the limit as x is approaching infinity of x divided by x minus the square root of. Now, keep this in mind. The square root of x squared is x, right? So if I'm dividing by x on the outside, then on the inside, inside the radical, I'm dividing by an x squared. So that we have x squared divided by x squared minus 3x divided by x squared. Okay, we have factored out an x. So I have the limit as x is approaching infinity of x times 1 plus the square root of 1 minus 3x. Okay, we now have a product. We now have something we're multiplying it by. So let's go ahead and use that trick again. So let's take x and rewrite it as 1 divided by 1 over x to create and force a fraction. So we now have the limit as x is approaching infinity of, for x, I'm going to write 1 over x in my denominator. And in my numerator, I'll write that other product. So I have 1 plus the square root of 1 minus 3x. Okay, now since I have a fraction, I can go ahead and apply L'Hopital's. L'Hopital's rule. Oh. Okay, so let's go ahead and do so. Before we do, let's go ahead and rewrite our function. So let's rewrite that 1 over x, or in other words, let's replace 1 over x by t and the limit as x is approaching infinity to the limit as x is approaching 0 from the right, or from the positive side. So that we have the limit as, well, not x, but rather t is approaching 0 from the right of t over 1, well, in the numerator I have 1 minus, was it always minus and I just wrote plus? Yeah, it was always minus and I wrote plus. I am so sorry about that. Minus the square root of 1 minus 3t. That was supposed to be 3 over x the whole time. Okay, so now I can go ahead and apply the derivative, apply L'Hopital's. So that I have the limit as t is approaching 0 from the right, you get 1. And the numerator, we just have to deal with chain rule. So we have negative 1/2, 1 minus 3t, take the derivative of the inside, which is negative 3. And we subtract 1 from our exponent of 1/2, so we have a negative 1/2 in the exponent. If we rewrite it, this is denominator of 1 of 3 divided by 2 square root of 1 minus 3t. Okay, let's go ahead and substitute in the 0 so that we have 3 divided by 2 square root of 1 minus 3 times 0 all over 1. We're left with 3 over 2 over 1, which is just 3 divided by 2. All right, that's it for L'Hopital's. In section 4.7, one piece of advice: do not confuse L'Hopital's with quotient rule. I know we're working with division and derivatives, but they're two different cases for two very different situations in the course. All right, thank you.